So today we're going to finish our review of threads. And then before we get started, though, I did want to take a moment to call out what you'll be doing for the Module 2 solution. There is an adaptation related to services and processes that we've picked up in a few other courses. And essentially, everything you're going to do in the Module 2 solution is to work with native resources. So what we want you to do is to explore native resources and the things that don't require any special tools, right? And then we want to pick up some lesser known PowerShell and command prompt resources to examine services and running processes. And then we're going to touch on the first aspects of sysinternals, but go in for a deeper dive in the Module 3 solution. We're actually going to be using it to resolve and to troubleshoot and that kind of thing. So in this module solution, you will basically use sysinternals as an adjunct or to supplement native tools just to investigate and to make quick observations. But then in Module 3, we take it to a whole nother level. Are there any questions about what we've just shared with you about the Module 2 solution? You'll see this posted in the module right after our session ends. Good morning, Deanna. How are you?
Good morning. I'm doing well. And yourself?
Pretty good. Are you hearing the audio okay?
Yeah, it's good.
All right. Very good. So let's continue with our let's let Tommy in. Good morning, Tommy. How are you? Long time no see. Have you been catching some of the recorded sessions we've put online?
Yeah, I've been following along.
I know you've been juggling quite a bit, so.
Yeah, my bad.
Oh no. I mean, the fact that you're multitasking and covering a lot of responsibilities is not a bad thing. I'm just glad to hear that you've had a chance to check out the videos we've been posting. So I've been trying to keep up with those and get those out sooner. I wanted you to know that constructive feedback from student evaluations of instruction at the end of the semesters is taken seriously, and we are working adjustments. So you have some subtleties of use of the fork and exec. So you use two different versions of fork in Unix and in some distributions of Linux. Exec is not affected the same way. So the whole point of this slide is with regard to threads in some Unix and Linux distributions, you have two different versions of fork. And exec works as normal. It replaces the running process, including all the threads. So remember, when you're duplicating a running service, fork and exec spawn off a new process. Everybody remembers this, yeah? Yes, no, maybe?
Yeah.
I do,
But-
yeah.
Does everyone remember the two basic forms of IPC? You have shared memory, and what was the other? Something about messages, right? So if you're looking at a message scenario for IPC, signal handling requires some attention, especially when you start working with threads. So every signal, so signals are a convention used to basically to help manage the IPC that's done with messages. And a signal handler, and there's more specifics here. The thing to remember is that it's typically utilized in user-defined context, not kernel mode. Any questions about signal handlers? The thing that you want to remember is that events are tied to this. So a lot of times a process is watching for an event. And in order for a process to be notified that an event has occurred, you have to have signal handling. But it's sensible when you think about it. When you're designing operating systems and message-based IPC, you do need to resolve specific questions, especially in a multi-threaded context. You know, when you're signaling in a multi-threaded context, there's a delivery interests. So, of course, you want to deliver the signal to the thread for which the signal applies, right? But there may be selected threads or every thread in the process, depending on the scenario. So that's part of the decision-making process when you're designing message handling. And so that's just one of the dynamics of single thread versus multi-thread. Part of thread management is being able to stop or halt or cancel a thread. So the two general approaches to thread cancellation are immediate and deferred. So you're checking if it should be. Now this implies that there are conditions or events in the mix, and that's, it's not explicitly stated, but when a thread cancellation is issued, the thread that receives it is called a target. So if you see a reference to target thread, that's a thread that's being targeted or canceled, right? Asynchronous means we're cutting it off immediately. It's a hard stop. Deferred, we're periodically checking. What are we checking for? Conditions or events, right? And remember that pthread is an implementation standard, and it's not a defined method to implement threads. It's a standard on how best to go about it. Well, what you see here is is a basic example of how to use that pthread standard. So here you have a specific example of the creation and cancellation of a thread. Any questions? Are we good so far? We're almost done with threads, or at least this chapter.
Good.
So thread cancellation. I mentioned conditions, didn't I? So, or events. So an event can be a change in a thread state, or it could be some event between threads, right? But essentially, when you're talking about thread state, there are dependencies. One of the things that we showed you early in module 1 was that services in Windows, and this is also true in Linux for daemons, there are dependencies. So you can have a thread state that changes, and this becomes an event for a dependency with other threads and other processes. So a change in state can be considered an event, and then there are other actions that play out based on the change in condition. And so the default type is deferred. So usually when you're working with, and this, the fact that the default type is deferred is one of the banes of memory and process management. It's not uncommon to have operating systems that have a lot of daemons or services that are running in the background that just aren't needed. And that's because the thread component of that process, it doesn't take out the trash, so to speak, preemptively. It kind of leaves it handy in case. So a lot of systems start up and they leave things running in the queue, especially when there's plenty of memory and plenty of CPU core to handle things. So it's the deferred type that's more common, but that gets messy because you have more services that are kind of watching and waiting, and they may or may not be needed. Remember that in terms of IPC, the messaging method, not shared memory, but messaging method is more common. And so when thread cancellation occurs, it happens through a signal, and that's just what we've related here. Shanoa is joining us. Good morning, Shanoa.
Morning.
How are you?
Fine.
Glad you could join us. Remind me at the end of the session to mention what we shared about the module solution, okay? So, thread local storage. This gets back to the way that you structure resources for multi-threading situations. If you have thread local storage, it means that you have dedicated copies of the data. And of course, that it incurs more overhead. There's more resources. It's useful when you don't have control over the thread creation process, meaning there's a thread pool and it's an on-demand kind of thing. It's automagic. Remember, we were talking about thread pools as sort of being it's like autopilot. So there's less intentional control over what and how things happen with threads. Thread local storage is often confused with local variables. We've talked about local and global variables before, and it's not the same as local storage. We just want to make sure everybody understands it's a different context, right? Any question about TLS? Schedulers have triggers. So a scheduler can be triggered based on time, or it can be triggered based on event. You can schedule resources based on happening or a condition in it, or they can be time driven. Okay. So this is just some quick detail about how that happens. Notice the relationship between kernel thread and user thread, and the intermediate process between the user thread and the kernel thread is this lightweight process. It's a method to translate lower level resources into application resources. When you have an interest that propagates from the kernel thread to the user thread, it's called an upcall handler, right? So whenever you're moving from the kernel to the user, a lightweight process is executing an upcall handler. So it's from lower privilege to user. So here's a brief review of some examples, first of Windows and then Linux threads. Any questions at this point?
None for me.
So just as you have a process ID, you also have a thread ID. That's really important as a concept because it's how you reference processes when you're trying to manage them. If you don't have process ID or thread ID in the mix, you see a lot of folks flailing about with their operating system interests because they don't know where to start. Just remember that a process ID and a thread ID is the practical index when it comes to commands and management. So just as we have specific components for a process, in Windows you have 4 different components. You have the thread idea, the register set representing the state of processor. When we say register set, we're not talking about registry, we're talking about memory register. Separate user and kernel stacks for when the thread runs in user mode or kernel mode, and private data storage used by runtime libraries and DLLs. So register set, stacks, and private storage area are known as the context of the thread. So these are memory components, right? You talk about the context of the thread, you're talking about what's loaded into memory. These are the different types of threads that you find in a Windows operating system environment: E thread, K threads, and TEBs, thread environment blocks. The so I want to say this is more on the user level, and this is down lower, of course. Any questions about what we're looking at? So essentially, the execution and kernel threads are in the kernel space in terms of memory, and the TEB is in user. So it's always fun when you're dealing with Linux. You're not dealing with a service or a process, you're dealing with a daemon. And by the same token, threads are called tasks instead of threads. So if we say task, you see references to task. In system calls, where that's a thread, it's a thread construct. Oh, that's one thing that keeps life interesting. It's one reason why POSIX came about, because people were getting so confused between the two different environments that at one point everybody said, hey, why don't we get on the same page? But you'll often see within the context of daemons reference to tasks. So we've talked about cloning before and parent-child scenarios. Any questions about Linux threads?
No questions.
That's it. So that concludes our review of threads. What we're going to do now is take up chapter 5 and get as far with that as we can. The goal is to complete our review of the content from those 3 chapters. And then if you haven't had a chance to check out the study guide, there are some things that are translated, if you will, for lack of a better description. So the stuff that's in the textbook is restated, and most important and relevant things are called out. So we just talked about a difference or a distinction between threads and tasks, and here you see task struct. So that's a Linux thread, right? As opposed to Windows. So this is where you get most of that essential information out of the slides in plain English. So please take the time to do that. There's also an addendum that relates some additional information, and does that in the context of virtualizing hardware. And there's also additional information about how you identify what runs in Linux as a daemon. So you'll often hear people talk about, Telnet is a service that runs, that allows people to connect to a CLI environment between systems across a network. Telnet is inherently insecure, but it's still used quite a bit, especially in private internal networks. When Telnet is active and it's available, that's because the Telnet D resources are active, right? So the D stands for daemon. So anytime you see a D stitched on the end of a Linux service, it means, oh, okay, that's actually the daemon that's active and running. So if you haven't already, take the time to check out what's listed in the study guide and addendum. And if you see anything in red and yellow, of course, make sure of that, right? Make sure you take the time to read that carefully. You should have copies of chapter 3 and 4 slides in the references and or resource folder. I'm going to go ahead and get started with chapter 5. So when it comes to concurrency, you can't really work multitasking and concurrency effectively unless you have a way to manage CPU scheduling. So at this point, we've been focused on the running tasks or processes and threads. And if those are so many plates that are spinning in air, the CPU scheduling has to do with how and in what order the juggler is working with those spinning plates, right? To borrow from an analogy we've used before. So let's look at some basic concepts and then scheduling criteria and some algorithms, how this works with threads in a multiprocessor context. We'll have some operating system examples and look at some algorithms. So whenever you have multitasking, multi-user operating systems, you have to, a piece of the critical, one of the critical things you have to have in the mix is effective CPU scheduling. Otherwise, you have a whole bunch of trains in a train yard and a lot of train wrecks, or you have a lot of intersections and in busy cities, and you have a lot of car crashes. I hope that makes sense. The goal of CPU scheduling is to maximize CPU utilization. Now, last week, I mentioned, or it might have been Tuesday, I mentioned that there's a graphical view of CPU cores that would tell you whether your CPU is being utilized efficiently or not efficiently. How would you know a CPU cores are not being scheduled efficiently based on what I shared with you earlier? Does anyone recall the simple resource you can use to get a quick gut level check on whether or not CPU scheduling is happening like it should? In a Windows system, what's the common resource you can use to take a look at CPU activity?
Task Manager.
Yes, thank you. You start in Task Manager, but then it's also helpful. Excuse me, helpful. It's helpful to open up the resource monitor and then to hit the CPU tab. And if you see a case where your CPU cores are showing differences, that would tend to indicate that the CPU scheduling isn't all that. Moving right along. On a hardware level, when you buy a CPU, has anyone ever heard of a Threadripper CPU?
I don't believe I have.
You don't believe you have, or you do believe you have?
I don't.
It is a very capable processor that's been manufactured by AMD. They have many cores. So for people who are performance enthusiasts or gaming enthusiasts, having a system with a Threadripper CPU is a big deal. In any case, both Intel and AMD CPUs, when you buy them, they have a base frequency and then they have a burst mode frequency. So you'll notice here in Task Manager, it's at 1.9 gigahertz. That's the base frequency or performance level of the CPU. But you can get changes in the speed. That has to do with something called burst mode. There are cases where you need to improve performance in order to handle incidental needs as they arise. A lot of times when processes or services are firing off and you're multitasking, there's large amounts of data that's flowing back and forth. So this is something that has to be built in to CPU scheduling capabilities, because otherwise it's painful and it's slow. This is something they've learned over decades. But I hope that explanation of this is sensible. I want you to notice this pattern right here. Can everybody see how an IO burst and how we're waiting on the input output? There's kind of a bottleneck, right? And then what happens? Well, you have a file system and that kicks into gear. And when the file system is reading and writing from disk space, the CPU cycles have to ramp up to handle that, right? So you have this pattern where you have intermittent cycles of CPU burst and IO burst and CPU burst and IO burst. That's kind of normal. It's sort of fun to watch servers in a data center, especially if they have LED lights on the disk arrays and memory access and stuff, because you can kind of see this thing play back and forth and back and forth. That's just from personal observation. When the CPU is running those file system calls, that's when the data can be read and written. So technically speaking, when a program requires a lot of data exchange, the CPU kicks into gear and then it's followed by that IO burst. So until the IO kicks into gear, there are interrupts that are in playing. Everybody remembers the term interrupt, yes?
Yeah.
Okay, so an IO delay would involve a construct known as an interrupt, among other things. And that's an oversimplification, but I just thought I would mention that. I'm going to keep trying to draw in concepts from our first module. So this is just a quick graph of what happens to the CPU frequency or cycles, right? So frequency is number of cycles per second. as each calculation cycle spins off, it's increasing the frequency of a chip. By the way, does everyone know how they separate or classify chips at a fabrication facility when they're making Intel I-Core chips and AMD chips? Does anyone know or recall from computer architecture how the factory determines, oh, this is a 4 gigahertz chip, oh, this is a 1.6 gigahertz chip? Does anyone remember in terms of the physical hardware? It's the amount of impurities in the silicon. So the dye that's used to make the chip, if there's more impurities, when they run tests on it, they find out that it heats up too much. So the reason that chips are rated for a lower number of cycles is because, oh, this batch in the factory has more impurities. So these are 1.2 gigahertz chips we're going to use in a MacBook Air, as opposed to 3.6 gigahertz chip we're using in a MacBook Pro. Does that make sense? And while we're at it, can we loop in some relevance here about overclocking? Please tell me you've heard the term overclocking before.
Definitely.
Say again?
Definitely have.
Definitely, you have, yeah. So what is happening on a system board when you're driving the CPU to overclock it? Simply put, what you're doing is using the motherboard and the system clock to drive a chip faster for its performance cycles than it is intended or engineered to perform. Understandably, you're going to have some data corruption if you're not careful. And the cooling requirements for the CPU chip are greatly increased when you overclock. So on gaming systems where performance is critical and people are pushing or overclocking a CPU so they can run up the burst capacity, right? A chip that has more impurities in the mix, in the silicon die itself, is going to overheat. So it's not uncommon in that context for gamers to build custom systems with water-cooled CPU coolers to try to keep that intact or under wraps. Any questions? Of course, if an operating system was better tuned for a given set of tasks and the CPU scheduler was custom built for a specific scenario, you'd have fewer issues. So, so here you see some basics about CPU scheduling. It's how it switches from a running to a waiting state, from a running to a ready state, from a waiting to a ready state. Everybody remembers that from last module, right? Where there was a difference between waiting and ready. Might be good to go back to that. Preemptive versus non-preemptive. So when you're working preemptive scheduling, it's usually in a context where there's shared data. There's a lot of activity on the kernel level, and there's a lower level critical hardware activity, including interrupts, right? So preemptive CPU scheduling is kernel mode. Non-preemptive would be the kind of stuff that happens for the user mode, application layer. Does that make sense? Do you get the sense from the do you get the sense from the term preemptive that that's like priority and non-preemptive is sort of like Yeah, it's on demand as needed. This is like, oh, this is, these tasks are going to happen. These activities have priority. Well, these we schedule as needed, right? So I'm just trying to talk around the concepts and in other terms to help clarify a distinction here. Short-term scheduler, right? So a CPU queue. Everybody remembers the static cache in a CPU? You have memory registers directly in the CPU, but then you also have like an S1, S2, S3 cache. Kind of, sort of, maybe. Hardware level. So how does that manifest in an operating system context? You have higher priority, quicker turnaround interests that play out in the S1, S2, and S3 level caches. And those make use of the short-term scheduler. So a dispatcher module gives control of the CPU to the process selected by the short-term scheduler. So a short-term scheduler says, hey, I need that resource on the CPU, and the dispatch modular gives control of the CPU to the short-term scheduler, where there's context switching and user mode switching and a lot of switching between memory address resources, right? So dispatch latency is the time it takes for the dispatcher to stop one process and start another. And this is a performance issue because whenever the dispatcher is changing context and user modes for the CPU activity with the short-term scheduler, it's overhead. So there are delays, right? Kind of makes sense. Think about traffic in a major metro area in a city, right? So you have a lot of start-stop at intersections, and that involves latency. There are delays. So the quality of CPU scheduling, one of the metrics is CPU utilization and throughput and turnaround time, waiting time, and response time. The quality of CPU scheduling is readily assessed by what values you see on these 5 criteria. So if your CPU is being fully utilized, there's lots of throughput, there's short turnaround time, there's less waiting time, and quick response time, then those are all indications that I mean, this is just kind of common sense, but these are the factors that operating system developers work with intensely when they're tuning kernels, when they're redesigning OSs for specific purposes. And I have to say that this probably happens more in the Linux arena than it does in the Windows and Apple. A lot of computer engineers and computer science professionals would argue that point and say, no, that's not true. But Microsoft and Apple are trying to provide an operating system that is generically useful for a wide range of interests, as opposed to Linux professionals who are tuning the kernels for specific performance scenarios. LAMP is a good example of this. So you have an operating system, a distribution of that operating system that's embedded and it's tuned for use with web servers. So how the CPU scheduling is managed in that scenario can differ depending on the context. So when we're talking about those different contexts, obviously you have differences in the algorithms that are used to execute that. And the same kinds of criteria are in the mix for that algorithm. Any questions? So what we're going to do here is take a look at some different scenarios, right? First come, first served scheduling. So a Gantt chart is a simple graphical representation of process and duration. So you'll notice here, process 1 occurs over 24 intervals. Now, when I say intervals, those could be nanoseconds, microseconds, milliseconds, all of that. Depending on the performance of the CPU, what we're talking about. It doesn't usually refer to whole seconds. Does everybody understand what I'm saying here?
Can you repeat? I just got back in.
Okay. So this is one of the methods for, well, this is one of the algorithms that are used for CPU scheduling. And essentially the first come, first served scheduling algorithm for CPU scheduling. And on this slide, they use a graphic organized, a way to graphically organize the process, right? The algorithm is called a Gantt chart. And a Gantt chart shows a task with a certain duration. So, I mean, generically, in computer science, the first process takes 24 time intervals. My comment was, everyone realizes that these time intervals are like in milliseconds or microseconds or nanoseconds, right? They're very small time intervals depending on the performance and how old the CPU is, right? So the waiting time for P1 is 0 because P1 commences immediately. Does everybody see that?
Yeah.
The waiting time for P2 is 24 time intervals because you got to finish with P1 the whole time. And then when that ends at 24, now P2 can take a turn, right? The waiting time for P3 is 27. So it's a basic timeline with start and stop, right? So what's the burst time for P1? Well, what they're asking is how much time intervals are used, right? So in this case, 24, in this case, 3, and in this case, 3. Because we start at 24 and end at 27, and start at 27 and end at 30 for P2 and P3. Does that make sense?
Yeah.
Now, one thing I want you to understand is that the average waiting time, let's say that you have 3 different processes that have to fire in sequence in order for an entire interest to be taken care of, right? Whenever you have a process that takes so long up front, that creates performance lags and bottlenecks and so on. So if you take your average wait time 0, 24, and 27 and divide by 3 for the 3 processes together, the average wait time is 17. So you have these different statistical metrics to consider. Let's look at the other algorithms. So let's compare first come, first served All right, so they're going to explain a little more about this. Suppose that the processes arrive in the order P2, P3, and P1. So now they're saying with a first come, first served scheduling algorithm, let's pretend or suppose that instead of the processes cleanly executing in a defined order, and why would that happen? I don't know, because you decide to open up a new browser tab and check on something else instead. The multitasking interests of any computing system vary depending on the users, right? So they don't happen in just a clean fashion like this. So if you're using FCFS scheduling, first come, first serve scheduling, and the processes arrive out of order, now the wait time for P1 is 6, because these other tasks are starting and ending. The wait time for P2 is 0, and the wait time for P3 is 3, because you got to get all the way through the second process before P3 can execute. So if the processes arrive in this specific order, now the average wait time is what? 3 time intervals. So what are we talking about? There's this, I want to call it a scenario deficit. It's based on the case for use. If you have a long process and you have a lot of shorter processes that happen afterwards, we talked about a bottleneck. The term for that is convoy. Think of a very long tractor trailer truck, and there's a very long tractor trailer truck, and it has a very long trailer, and there's a couple of smaller cars behind it. They're kind of stuck behind it, and it's like they're in a convoy. If the cars can get out in front of the tractor trailer truck, then it's a much better scenario. So CPU bound versus IO bound. P1 can execute after the CPU is finished with P2 and P3. That's a case where it's CPU bound. This is a case where it's IO bound, meaning the delay in total IO for all of these processes is delayed because you have one really long process and the others can't perform their IO until you wait for it all the way to 24. So you're IO bound, meaning you're constricted by access to IO because you're waiting on this first process to be done. And in this case, this process is waiting to get started while the CPU is firing off the IO cycles here for P2 and P3. So you can have computing scenarios where the load is greater or the bottlenecks are greater with CPU versus IO. Okay. Is it possible that you could get an assessment item showing this kind of scenario? Yes. So when we talk about CPU scheduling, what is it we want you to have an appreciation for? The fact that IO and CPU are interrelated, and in order for any input output of data to occur, you have to schedule the CPU, and how that executes can be profoundly different based on the scenario. Shortest job first. Now, you can associate with each process the length of its next CPU burst. Use these lengths to schedule the process with the shortest time. So what are we saying? First come, first served means whichever process is asking for the CPU gets the CPU first. And there are trade-offs, and we just discussed those trade-offs. Well, what happens if you have these three processes and you say, okay, I'm going to go shortest first? That's another CPU scheduling method, right? SJF is optimal, gives minimum average wait time for a given set of processes. The difficulty is knowing the length of the next CPU request. Could ask the user. So what are we saying here? Well, if you have a lot of short tasks, SJF is optimal. So it gives the minimum average waiting time for a given set of processes, but there are scenarios where that's not the case, right? And if you can't anticipate the next queue cycles, that's a disadvantage. So let's take a case where you have 4 processes, and the burst time for each is listed here. So if you take the shortest process first, that would be P4. So if you're executing SJF as a CPU scheduling algorithm, the CPU says, hey, I'm not taking the first one that shows up, not first come, first serve. I'll take the shortest. The next shortest is 6. So I have P4, then P1, then what? P3, and then P2. So the average wait time is 7. So here's some interesting math about how to determine the length of the next CPU burst. So the preemptive version is called shortest remaining time first. We're not going to spend a lot of time in the weeds with this. The important thing to understand is that being able to assess the length of the next CPU burst can help can be useful for an operating system, because CPU scheduling methods, different CPU scheduling methods could be implemented based on the context. Now, why would you care about CPU bursts and prediction? Does everybody remember the 80-20 rule?
Yeah.
So I just wanted to provide some relevance here. Why should you care about the ability to predict the length of the next CPU burst? Well, if you understand the types of data and the amounts of data and the active processes and services that are working that data, and you understand when and how or to what degree the next CPU burst occurs, you can do some creative things with caching, memory caching, where the stuff you need most is stored preemptively. Does that make sense? So the 80-20 rule means you're going to use 20% of your tools 80% of the time. Or if your users are working with a brand new operating system, of all the operating system features, they're going to use 20% of those features 80% of the time. Right? The whole idea of caching and improving performance basically depends heavily on the ability to predict the length of CPU bursts. So this is one aspect of how, if you want to enhance CPU scheduling, this has to be a part of the scenario. So what you see here are examples of exponential averaging. Again, this has to do with CPU burst prediction. It's just useful to understand that this is a performance enhancement capacity interest. So if you have CPU scheduling that does not include the ability to predict CPU bursts, then there's a lot of other performance added features that just don't work very well. Shortest remaining time first. So if you are predicting CPU bursts and then you use shortest first, the shortest is 1. If I'm looking 2, 4, is it just me or am I seeing 1 again? So burst time and arrival time. Let's look at this chart for a minute so we can kind of suss out what's going on here. If P1 is executing first, basically, yeah, I'm wondering if there's something off about this Gantt chart because it's showing 4 processes, but it's showing the P1 a second time. Let me research that. I don't want this to confuse folks about what's going on here, but as an example of shortest remaining time first, I don't know that I would try to represent that this way. So when you're working with CPU scheduling and you need to manage priorities, lower priority processes may never execute. So when we're talking about preemptive versus non-preemptive, everybody remembers this?
Yeah.
Okay. So we're talking about priority. And when the low priority processes never execute, that's called starvation. And as a process ages, its priority increases. So priority scheduling is a way to ensure that there's a balance between preemptive and non-preemptive processes. So what are we saying? Let's say that there's a low priority process and it's not getting any attention. It's not getting any attention. It's not getting any attention. For each cycle that it doesn't get play with the CPU, its priority is increased iteratively, right? So as you age a process, its priority increases. So it gets, eventually at some point, it's going to tip the scale and then, and then it gets time with the CPU, right? So that solution is referred to as aging. So as the low priority process is ignored, its priority increases with age, with each time interval. So aging is a progression of time intervals, if you think about it conceptually, right? Any question? So this is an example of priority scheduling. So here you see that P2 is scheduled first because it has the shortest burst time, right? And then P5 is scheduled next, and that's because its priority is 2. Well, all right. So we're not using shortest first, but yeah, so this is an example of how we're not doing shortest first, and this is why P4 is at the end of the line. It's got the lowest priority. So this is another type of CPU scheduling algorithm. It's based on priority, and so what you're seeing here is a case where it's not about the shortest process being scheduled first, but it's about the highest priority one. And in this case, P2 has a very short burst time, and P4 has a very short burst time. And if we were using the SPF method, P2 and P4 would be like right here, neck and neck. But instead, you see P4 is at the end of the line because it's got the lowest priority. Does that make sense?
Yeah.
Okay. I think what we're going to do is stop before we get into round robin. Okay. So we'll stop here with this quick review we did of priority scheduling, and before we get into round robin, we'll pick that up on Tuesday of next week. In the meantime, between now and Tuesday, if you would, please be sure to go back onto, I was going to pull up Blackboard. Go out on Blackboard and get started with the Module 2 solution so that you can use some tools to investigate and just investigate and assess some of the features and criteria we've reviewed with in this module. So what am I saying? You get in there and you're investigating basics or essentials about services and daemons. And those are things like the priority level of the service, the dependencies of the service. There's interests that relate to the PID, right? So the solution in this module is designed for you to just see how you can use these tools to collect basic information about processes and daemons. By the next module, as we said, you'll be doing a lot more elegant troubleshooting and analysis with sys internals, but that's after we cover some more concepts. Unless there are other questions,